Fabio for giving me a chance to come here. This is the first time to visit Brazil. I'm enjoying the school and the atmosphere and perhaps food. Okay, so today I'd like to talk about some recent stories about high energy cosmic neutrinos, which were discovered a couple of years ago. Okay, so motivation is that, okay, neutrinos, the birth of the neutrino astrophysics happened many years ago, and then we detected neutrinos from the sun and supernova 1987, which led to the Nobel Prize in 2002. And also, recently, because of the discovery of neutrino mass, here's a study of the neutrino oscillations, and then Nobel Prize in 2015 went to the super candidate and the snow experiment, and then especially the super K that measure the neutrino oscillations using the atmospheric neutrinos. And atmospheric neutrinos are produced by cosmic rays in the atmosphere. Then when the Kohta-san won the Nobel Prize, he says that I want to thank the neutrinos, of course, and since neutrinos are created by cosmic rays, I want to thank them. A good word. However, yes, so we want to thank the cosmic rays, but unfortunately, we don't know, what they are exactly. So we measure the cosmic rays over the wide energy range from the GeV, 10 to the 9 electron volt, to the 10 to the 20 electron volt. So the 10 orders of magnitude, and then we see we don't know the power spectrum is described as power law. Then roughly speaking, the 2.7. Then if you go to high energies, and the spectrum is steeper, and then around the 3 eeV, the 3 times 10 to the 18 electron volt spectrum is hardened, and it's the minus 2.6. So basically is it's described a power law with some structures. So people believe that the cosmic rays up to the near energies come from the galactic sources. The most promising candidates are supernova remnants. And then, but if you go to higher energies, especially the 10, around above the 10 to 70 electron volt, which actually corresponds to the energy achieved LHC, because the Large Hadron Collider, the center mass energy is 14 TeV. So if you perform the Lorentz transformation from the center mass energy to the Raman energy, this corresponds to the 10 to the 17 electron volt. Then above these energies, yes, we don't know, but especially above the energies around the ankle, people believe that the cosmic rays come from the extragalactic space because it's difficult to confine such high energy cosmic rays in our Milky Way. And the question is that, okay, how this spectrum formed, where the transition from galactic to extragalactic components happen, then how the cosmic rays are accelerated, and how do cosmic rays propagate. But in order to address these problems, especially for the extragalactic cosmic rays, and we would like to know we need to understand what is the origin. We need to address this question. So we don't have good promising the candidates for the ultra-high cosmic rays. Basically, it's bad. There's some theoretical arguments, so-called Hiras conditions. So this is the x-axis size and the y-axis magnetic field. So in order to produce ultra-high cosmic rays, at least you need to confine the cosmic rays in the system, right? And then one of the necessary conditions is given by the Raman radius, which is given by the energy over EV, and then is smaller than the size, system size. This is R. And then if you look at the possible candidates, and actually not so many sources can satisfy this condition. Okay, so you see the many, but actually there are degeneracy, and because they discuss a different acceleration site. So for example, if you look at the candidates, so the magnetars, which are the stars with the strongest magnetic field, the magnetic field can be 10 to the 15 Gauss. And then gamma burst, which is the brightest explosive phenomena, then luminosity can be around 10 to the 51 erg per second to 10 to the 52 erg per second. And then AGN, this is the most massive black hole object. And the Galactic cluster, which is the largest gravitational bounded object. So you need some extreme object. It's something like a cosmic monsters, and we need something extreme. So what we know about the ultra-high cosmic rays, and yes, so recently the telescope array and the Pierre Auger observatories measure the cosmic ray spectrum. In particular, Auger has a lot of statistics, and the spectrum is measured, and you see that around the ankle, and the spectrum is hardened, and also around the 10 to the 4 times 10 to the 19 electron volt, 4 to the 5 times 10 to the 19 electron volt, you see the suppression. And this is actually consistent with the pictures that the ultra-high cosmic rays interact with cosmic background radiations, including the CMB and extragalactic background light. Also, there's another possibility that just maybe related to the maximum energy of the sources. And then compositions, yes. So it's under debate. The Auger results suggest that the composition is heavier at highest energies. And then one more important information is anisotropy. And this is actually in order to identify the sources, actually we would like to see some anisotropy, especially at small scales. But so far, we have not had established anisotropy yet. However, the important progress which recently happened is that the discovery of the dipole anisotropy, which already exceeds 5 sigma. And then, the center of the dipole is not far from the center of the galaxy distribution, which supports that the ultra-high cosmic rays come from the extragalactic sources. OK, so we'd like to identify the sources of the extragalactic cosmic rays. But as you see, that problem is that if you want to use the galactic cosmic rays only, they are charged particles, and then they are intervened by the magnetic fields, including the extragalactic magnetic fields and the galactic magnetic fields. And it's not so easy. In the sense, it's kind of important to use the neutral particles, including neutrinos and gamma rays. This is a multi-messenger approach to the cosmic ray sources. However, the gamma rays, you have another problem. Because, if you want to ask the extragalactic cosmic rays, the energy of the neutrinos gamma rays can be quite high. But this is the energy. But the very, very high energy gamma rays can interact with the cosmic background radiation. And then you see that if you go look at the 10 to the 15 electron volt photons, mean free path is order of 10 kiloparsec, and just galactic center. Okay, and then even around 10 TeVs, basically the mean free path is around 300 megaparsecs. So the photons can propagate only, cannot propagate with the cosmological distance, such as gigaparsec. So in that sense, the neutrinos can be a unique probe to probe over the extragalactic cosmic ray sources. And then how you can find such high energy cosmic neutrinos. And then one of the proposals is made by Markov, and in 1960, and he proposed that to install the detectors deep in the lake or sea, and using the Cherenkov radiation technique. So when the neutrinos come in, and then they hit the ice or water and make muons or other charged particles, and then this kind of Cherenkov radiations can be, if you can see the Cherenkov radiations, you can use this technique to find the high energy neutrinos. So, what? Freezing? What happened? OK. So, however, of course, difficulties come from the weakness of the neutrino interactions. And then, yes, so astrophysically, the neutrinos are produced by the pion decay, for example, and high energy neutrinos. And if we want to see these kind of neutrinos, then if you look at the neutrino nucleon cross-section, neutrons are protons and neutrons, And basically, this is the energy, and this is the cross-section. And this weak interaction is quite weak. But the cross-section increases as energy. And if you look at the cross-section at PeB, which is 10 to the 15 electron volt, you see that cross-section is order of 10 to the minus 33 centimeters square, which is much larger than the low-energy neutrino cross-section, but still much weaker than the electromagnetic cross-section. For example, Thomson cross-section is order of 10 to the minus 24 centimeters square, right? It's still much weak. And then, yes, so the neutrinos can interact with the nucleons via the charge current interactions or neutral current interactions by exchanging the weak bosons or the Z bosons. And then, but in any case, using this number, you can ask how big the should detector be, and then for the given flux. So this flux is some astrophysical flux, I just gave by hand, and then this is the cross section. You see, and then you can ask that this is Avogadro number, and this is the density, and in the case, you can put the density of the ice, water, and this is the volume. Now you can ask that what is how much the volume you need to find the cosmic neutrinos. For a reference flux, which is 10 to the minus GeV per centimeter square per second per terajon, you see that in order to see the neutrinos, 10 neutrinos per year, which is a kind of reasonable number, you need a 1 kilometer cubic neutrino detector, which is huge. Just in case we discussed, I introduced the super K. The fiduciary volume is about 22.5 kiloton, right? And then it's too small, so you need a much bigger detector. So this is then we have IceCube. Then IceCube, the gigaton neutrino detectors, they put the strings and the sus pole, and then the 86 strings, and with 120 meter spacing, then they have about 5,000 PMTs for the multiplier tubes, and then it was complete in the 2010. Then it's huge. You see that the size of FR is here, and you can imagine that how big the IceCube detector is. So how you can detect the neutrinos? So basically, you have three main event types. So the one important, these are two important detection channels. One is the upgoing track. So when muon neutrinos interact with ice, and then you have muons, and the muons actually go through the detectors and emit the Cherenkov radiations and accompanied by the Bremsstrahlung emissions and other energy losses. And then in this case, you can see the path track of the muons. That's the reason why we call tracks. Now, on the other hand, when the electron neutrinos interact with the nucleons via the charge current interactions or any flavor of neutrinos, electron neutrino, muon neutrino, tau neutrinos, then can interact with the nucleons via the neutral current interactions. In this case, you have hadronic showers, or you have the electromagnetic showers, or both. And in this case, these kind of charged particles eventually emit the radiations, and the photons are scattered or out. In this case, we see the kind of the more or less kind of blob-like emissions because of the photon scattering. And in this case, in the case of the tracks, because the muons go through, and the energy resolution can be as good as probably order of factor of 2. But angular resolution can be as good as 0.3 degrees at high energies or 0.5 degrees, and a bit worse at lower energies. And in the case of showers, because we see the kind of broad-like features, and it's more difficult to determine the direction. So the angular resolution is 10 to 15 degrees. It's OK, but not so bad, but not good. And then, but energy resolution can be good, but because you can see the number of photoelectrons. So then actually the energy resolution can be as good as 15%.
How do you calibrate the energy measurements?
Sorry?
How do you calibrate the energy?
Oh, so I think basically this depends on the ice properties. For example, in the IceCube people, they use lasers, or so they put some lasers and try to inject. And then you can calibrate the photomolecular tubes and the response. And the third channel is a double pulse or double bang event, which can be produced by the nu tau via the charge current interactions. When nu tau interacts with I, and you have tau leptons, but tau leptons are unstable. Eventually they decay and make showers. And in principle, if this kind of interaction and decay happens inside the detector, we see the two shower signatures. This is a so-called double bang. So what is the signal and what is the background? So so neutrinos are actually we want to see the astrophysical neutrinos, but our Earth makes a background, atmosphere, because cosmic rays hit the atmosphere, and you have muons, right? Because there are a lot of pions produced and pion decays, you have muons, and pions, muon decay, you have neutrinos. So that you have atmospheric muons, atmospheric neutrinos, and if you this is the IceCube, this is Salford. I flipped the Earth, and low energies actually it's very hard because you see a lot of muons. Basically, atmospheric muon rate is 10 to the 11 per year. It's huge. And in a sense, you might wonder that it might be very good to look at the upgoing events, because upgoing case muons are blocked, but neutrinos can go through, right? And then still you have a background atmospheric neutrinos, but in principle you can try to look for the astrophysical neutrinos in the background. But of course, these are they're both as important actually, because downgoing events is not good at low energies because of the atmospheric muons. But if you go to high energies, actually you can atmospheric neutrino flux, muon flux decreases very rapidly. Eventually you can look for the neutrinos from the other downgoing events. The upgoing events actually initially may be good, but you have because you can avoid atmospheric muons. But very, very high energies, it starts to be problematic because very high energy neutrinos, because you see that cross section increases as the energy, right? Then Earth becomes try to block neutrinos. For example, PV neutrinos, if you come from the opposite direction, the PV neutrinos cannot penetrate the Earth. They are stopped. So in a sense, this depends on the direction and the energy, and you need to think about what is the background, what is the signal. Sorry?
What percent is stopped by the electricity?
It depends on energy. For example, typically, if you come from if you consider these directions, optical depth is around unity, for the neutrino energy is around 30 TeV or something like that.
What percent is stopped?
In this case, exponential minus tau, that's the 30% at around 30 TeV. Then, of course, the cross section increases as energy. The tau increase. The high energy almost zero, becomes close to zero, and it's much smaller, kind of 1%, less than 1% or something. Okay, and then the IceCube started to complete it 2010. Then after the 2 year the full operations, and then they actually around 2000 in the 2012 in the Neutrino conference, and they reported the first discovery of the cosmic Neutrino candidates, Bart and Arnie, and then in the following year. And then following years, they found the 26 more events, and then basically using these 28 events, they reported the evidence of the high energy cosmic neutrinos, which was chosen the top #1 top 10 breakthrough in 2013. And then just to see the size of this kind of shower, this is I think Madison. And so you see that because size of the shower is order of 100 meters, right? And 100 meters, then you see that if you project it, quite big.
So what type of colors again?
The color is the timing. So the color is red is first, and then this is later. So when the photons are detected. When the neutrino hit, And basically, the event started here. Then, because of photon scattering, then basically the photons are detected later at a larger distance. And then size of the probe is actually represents the number of photoelectrons is deposited. And then, yes, this is a diffuse neutrino flux spectrum. And then, so I show the two different data sets. This is the high energy starting event. This is the mostly showers with some tracks. And then this is the upgoing tracks, muon tracks. This is, as I said, that the signals produced by the muon neutrinos via charge and current interactions. So yes, so at least if you look at the neutrino data about 100 TeV, they are more or less consistent. The important thing you should keep in mind that the flux of the diffuse neutrinos per flavor is order of the 10 to the minus 8 GeV per centimeter square per second stereo. But if you look at the data and compare the two data, the spectrum index actually look different. Probably because neutrino HESI data are more sensitive to the lower energy neutrinos. And then in this case, because of the data around these energies, the spectrum index is actually steeper than this. So at this point. But I would say that that these data are consistent with each other and within the uncertainty. Because if you compare this energy range, it's consistent.
What are the highest energies that were observed?
I think in the case of muon tracks, I think as the original neutrino energies, in the deposit energy 2.6 PeV, and then if you estimate the original neutrino energy, and I think the order of the 8 PeV or something like that. Is it right? Then that's Croppo. I think that.
I think the number is right, but there was one event in this year.
Oh, right, 9 PeV event. Yeah, 9 PeV events, yes, this year. But I think this event is not included in this analysis. That's the reason why. Yeah, in this data, the recent data, yes, recent one is actually 9 PeV event was there.
Are you still using Sesame Street names, or you stopped?
They stopped it, right? Still use the Sesame Street names. You guys stopped, right?
We stopped naming it.
Yeah, right. Yeah. Okay, and as I said, okay, so these are tracks and showers. And tau neutrino candidates is actually recently reported in 2018 the neutrino conference, and we found two double pass candidates, and which could be the charge current interactions caused by new tau. And as I said, tau decays with a lifetime of 3 times 10 to the minus 13 seconds. This implies that if you consider 1 PeV neutrino, and then basically you have a 50-meter separation before the tau decays. And then, yeah, in this case, it's a bit unclear. But in this case, you see the kind of the two pulses, and which can be, which looks a good candidate for the new tau. And another interesting news was, the report of the candidate of the glacial resonance event. So when the anti-electron neutrinos come in, the anti-electron neutrinos can interact with the electrons, and they make double bosons, and the double bosons eventually decays, and then about 60–80% of the decays are hadronic decay, so that you have showers. So in this case, this event is actually if you calculate the deposit energy deposit in the detector is about 5.9 PeV, and then if you do the analysis, our energy of neutrinos is about 6.3 PeV, which is consistent with resonance energy for this glacial resonance event. The glacial resonance here, when the electronic neutrinos interact with electrons, and the cross-section is enhanced. And then, yes, so you can also estimate the corresponding flux. Of course, one event with a big variable, but still consistent with the muon track result, which I showed in the previous slide. And then, because you have tracks and showers, right? Tracks actually come from the muon neutrinos, The showers come from the electron neutrinos and the pure charge current interaction, and then other flavors, all flavors with neutron current interactions. And you guys have Neutrino candidates, and using these informations, you can try to ask the flavor ratio, right? Using this information. Then yes, so that because neutrino has a mass, and the mass eigenstates are different from the flavor eigenstates. And if you calculate the neutral oscillations, and you could take the long baseline limits, long distance, the simple theory predicts that the flavor ratio among the mu e, mu mu, nu tau is 1 to 1 to 1. This is a simple expression if you ignore the complications. And here, this is here. And then data, recent data suggests that this point. And of course, you see that 1 sigma error is here, and then 2 sigma here, and the huge still the uncertainty is quite big, but this is consistent with the theoretical flavor ratio 1 to 1 to 1. Okay, so what is the sources? And then you see the neutrinos. This is the sky map. And in the gamma ray case, you have a lot of sources. But the neutrino case, basically, zero established source, except for one candidate. So yes, but so far there are fishy sources are reported. And yeah, so far we don't have established source, but none of the interesting candidates are found, but none of them are significant yet. But even though we have not found established source, actually you can ask what can we learn from the non-detections? Because we don't see the very kind of the clustering at high energies, for example, 50 TeV or larger, higher. And using these information, actually you can put the limits on the number density of the sources. Because if the sources are very rare, this implies that each source has to be powerful. In this case, you should expect that the distribution of the neutrino events are different from the kind of random distribution, isotropic distribution. You expect some clustering, maybe doublet, the pair of neutrinos, and triplets, and the three events in clustering. And but we don't see such the clustering at very high energies. You can put limits. And then using we actually measure the diffuse flux, right? This is what I showed. The diffuse flux is basically the line of sight integral over the Hubble distance, cosmological distance. So basically, it's proportional to the size of the universe and number density of the sources and the neutrino luminosity. So we measure the diffuse flux, and you can estimate the energy generation rate in the neutrinos. Then this is the 3 times 10 to the 43 erg per megaparsec per year. And using this information, if you show this band, the value in this band here, this red band, then you have limits from non-detection of the multiplet. And in order to explain the diffuse flux, any source has to be located along this line. Basically, this implies that rare sources, such as blazars, are unlikely to be the dominant, likely to be subdominant. And then, common sources, galaxies, clusters are still opposite brother sources. Sorry? Sorry. Yes, sorry. I'm going to explain later. So this is the active galactic nuclei, and whose jets point toward us. Sorry, and I'm going to explain next slide. Because in this plot, just for simplicity, I only show the steady sources. Supernova transient, yes, we have a plot for the transient too. But in this talk, for simplicity, I didn't show the supernova and other possibilities. OK, so now the multi-messenger stuff. And because this is the information you can see from neutrinos only, because now you have Fermi, the IceCube, and the OJ. And each of the experiments allows us to see the diffuse flux. So this is a diffuse flux measurement. And for the different messengers, this is the energy, and this is the energy flux. So the important thing is that, yes, particle energy is quite different. Basically, the range is from over the 10th order magnitude, but energy flux is actually comparable, right? So in the sub-TeV gamma ray flux, neutrino flux in the PV range, the ultra-high energy cosmic ray flux are 10 to the 18 to the 19 electron volts, everything comparable. And then this implies that somehow the energy generation rates of gamma rays, high energy neutrinos, and the ultra-high energy cosmic rays are comparable. So, however, we don't know neutrinos origin of neutrinos, cosmic rays, but at least we know the origin of the gamma rays more or less. So this is the extragalactic gamma ray sky. Then we see galactic plane. There are a lot of the extragalactic sources. And then we understand that the most of the extragalactic sources are actually the blazars. So the blazars are AGN with jet. And if you see the jet from the on axis of the jet, and then we observe that this kind of jet as blazars. And then these blazars, show the strong beam emissions, and we see the gamma rays from them. And then total gamma ray flux from the blazars, basically if you accumulate all the contributions over the cosmological distance, you can see that most of the extragalactic gamma ray background can be explained by the blazars. Now, in this sense, it's quite natural to ask that the blazars may also be responsible for the neutrinos, right? Because you saw that the energy flux is comparable. Then yes, so the blazars are discussed as possible neutrino sources, because in this case you have jet, and then cosmic rays are accelerated, and then basically the electrons are accelerated here. That is the VC gamma rays. But the cosmic rays can also be accelerated in this acceleration region. And once the cosmic rays are accelerated, very high energy cosmic rays can interact with photons and making pions. And then this pion decays neutrinos. And then that is why people anticipate that the blazars are good candidates of neutrino sources. And then I showed several predictions of the theoretical prediction of the neutrino spectrum. This is something like this. However, there are a couple of problems. As I already explained, the absence of the neutrino clustering itself, actually these papers are rare sources, including blazars. Plus, blazars are so bright, and you can see the blazars in gamma rays. You can do stacking analysis, right? Because you can use the Fermi data and neutrino data. Then basically you can try to correlate the two, the gamma ray neutrinos. And then this is stacking limits. And it's already below the data. And then the many theoretic curves actually predict a very hard spectrum. The IceCube do not see the very, very high energy events, above 10 PeV. And then they have upper limits in this energy range. Basically, many original predictions of the blazar neutrinos are excluded. So these three things actually disfavor that blazars as dominant bulk origin of the high energy neutrinos. Although I don't exclude that they contribute some of the diffuse flux. The similar reasons, gamma ray burst, it's a brightest object, but because gamma ray burst is so bright, you can actually do the stacking analysis, right? Gamma ray burst, neutrinos, you can try to address what is the contribution of the gamma ray burst to the diffuse neutral flux. We know that the contribution is less than 1%. So they have difficulty. And then the interesting possibilities, alternative possibilities are cosmic reservoirs. So basically the starburst galaxies or galaxy clusters. And in this case, basically the neutrinos are produced in the environment. For example, in the case of starburst galaxies, supernova remnants or other transient sources can accelerate the cosmic rays and inject the cosmic rays in the environment, in galaxy environment. And then these environments have magnetized, and the cosmic rays are confined for about a mega year to 10 mega year in the case of starburst. And then because then while they are confined, they can make neutrinos via the PP interactions, proton-proton collisions. And then in this case, in this sense, you can regard this kind of system the reservoirs of the cosmic rays. Then you can think about you can think about this analogy for the galaxy cluster environment. In this case, galaxy AGN can be a cosmic rays accelerator, but the galaxy cluster is so big, and the cosmic rays can be confined for many, many years, and the neutrinos can be produced. But the ultra high energy cosmic rays probably cannot be confined, and because high energies, they can just escape. and before they are subject to the strong interactions. So interesting thing is that people calculated the neutrinos from starbursts and galaxy clusters, and then the theoretical flux is actually the more, of course, Assad is quite big, but but theoretical flux is actually consistent with what IceCube sees. Basically, the order 10 to the minus 8 per GB per cent square per second per lambda. That's the reason why this kind of model is actually interesting as a sources of the high energy neutrinos. Okay, so now how you can test these kind of the models and using the multimeter data? Yes, so that you can explain the neutrino data based on these models. But the important thing is that you should not forget gamma rays, and then because when the neutrinos produce, the neutron pion there, and the pion decays gamma rays, these gamma rays are unavoidable. And then very high energy gamma rays, low energy gamma rays can just go to the come to the Earth, but high energy gamma rays, yes, in this case they interact with cosmic background radiations, and then you have electron-positron pair. But their energy do not disappear, right? Because energy conservation. Then eventually, these electron-positrons upscatter the CMB photons, and then again, the high energy gamma rays produced. And in principle, this kind of process repeats. And this is so-called electromagnetic cascade. And then if you compare the neutrino data and gamma data, as I said, that they are comparable. And at least if you consider the power of spectrum, you can learn that the spectrum index of any kind of neutrino source and cannot be very steep. Because, for example, if you put the spectrum index of 2.7, you immediately violate the Fermi gamma ray background. So that in order to satisfy the Fermi gamma ray background data, basically the spectrum of the neutrino sources has to be quite hard, less than 2.21 to 2.2. This insensitive the different assumptions. And also, you might wonder that, okay, it might be possible to have a physical connections between the neutrino data and the gamma data. This is also the possibility. So if you are interested in this kind of the theoretical possibilities, you can have a more brave. And in this case, you can wonder that is it possible to unify the neutrinos, gamma rays, cosmic rays? Yes, of course, in principle, this is possible. Although just simple, probably this argument is too simple. But just if you put the injection of the e to the minus 2 spectrum and the cosmic ray flux, then if you consider the reservoir models, the low energy cosmic rays up to the 100 PV are confined in some reservoir environment and making the neutrinos and the gamma rays. The ultra high energy cosmic rays, very high energy cosmic rays cannot be confined, then escape into the intergalactic space and making neutrinos and the gamma rays. And if you actually just combine all the informations, it's possible to that fits the neutrino, gamma ray, ultra high energy cosmic rays simultaneously in principle. This is a kind of too simple argument, but indeed, this is one of the examples based on the astrophysical models, and here I consider that we consider that AGN and embedded in the galaxy clusters, and just assume that AGN is accelerators of the ultra high cosmic rays, and then we actually simulate the fate of the cosmic rays, and the PB cosmic rays are confined and making neutrinos, and the gamma rays actually the high energy cosmic rays escape and then may contribute to the observed ultra high cosmic ray spectrum, and the cascaded gamma rays actually contribute the non-Blazer component of the extragalactic gamma ray background. So in a sense, it's possible to explain the three data in principle. However, this is interesting. However, the one issue exists. If you look at the neutrino data carefully, and yes, this model can explain the above 100 TeV data. But below 100 TeV, you see the kind of the bump. And actually, this kind of the high energy large flux is inferred in the recent data of the shower analysis. Basically, they look for the low energy showers, kind of sophisticated analysis for the shower data. And indeed, the flux is quite high. The few times 10 to the minus 7, around 10 TeV. So the spectral index actually might be steep. And the consistency among the different analyses still the kind of under debate, which might indicate the structure, but so far it's difficult to say. But the important thing is that the flux around 10 TeV is very high, 10 to the minus 7. So that if you repeat the game of the neutrino gamma ray connection, you can show that this is not so easy to explain if you assume that source is transparent to the gamma rays. Because if neutrinos here, again, the gamma rays should be produced, no matter the process is PP and P gamma. If you calculate the corresponding gamma ray flux, you can see that this gamma ray flux violates the gamma ray data. It's a problem. So this simply implies that in order to satisfy the Fermi gamma ray background, you need to require that the gamma ray has to be blocked. You need a hidden source. So we don't know the candidate of the hidden sources, and people discuss basically the different possibilities, including the chalk jet, where the jet is embedded with the star, or neutrino produced in the vicinity of the black holes. No matter what the model is, I would say that this kind of the hidden source is actually, in a sense, natural. Because if you look at the density, because if you consider such a high density environment, because the neutrinos, if the neutrinos are produced by P gamma interactions, same gamma rays, same low energy target actually is important for the very high energy gamma rays. And basically, you can always have a relationship between the efficiency of the gamma-gamma interactions per production process and the P-gamma interactions, the PAM production process. And then this is just to determine the cross-section ratio, which is the order of 1,000. So this implies that in order to have a efficient neutrino sources, automatically block the gamma rays. In the sense, actually, it's not quite natural that to invoke such a hidden source. And for example, if you look at this kind of model of for example, just an example of the AGN core model, yes, so it's actually you can see that it's possible to express this 10 to 100 TB data, and in this model. And a good thing for this AGN core model is that because we already measure the AGN, the disk spectrum, and the coronal spectrum, basically you have a kind of robust prediction in the MeV energy range. Basically, gamma rays cascaded down to MeV range energies, and which appears MeV band. And if this model is correct, then basically the future MeV gamma ray telescopes should see the gamma ray emissions from the SAIFR or low stage. Just I would like to show the one slide for the galactic contribution, so that I focus on the exotic interpretations. But in principle, you can think about the galactic contributions. Now, IceCube already put interesting limits on the neutrino flux of the galactic plane, but we don't, so far we don't have the many events from the galactic plane. Then typically the contribution is less than the 10% or something like that. However, the contribution from the galactic halo or big region is actually the more difficult to constrain. And then at least the neutrinos cannot, data not sufficient to constrain the data. And in this case, I would say that the multi-messenger data can be important because the gamma rays around, in principle, using the air shower experiments, cosmic ray experiments, you can actually have a limit on the gamma ray flux above the 100 TeV. And then as you show this, this data. Then you see that apparently there's a tension between the data and the theory, but the limits are not so good. And this implies that if there's a significant contribution from the big region in the galactic halo, and future gamma ray telescopes experiments can test this kind of possibility. Okay, so people also discuss the dark matter stuff. And then, neutrinos are actually produced by dark matter. And then, in this case, actually, this is a kind of model of the Pascal. And then you can also try to explain the neutron data and then the dark matter decay. But in this case, again, the gamma rays are again important, and depending on the final states of the decaying dark matter. And in the case of this kind of the model, especially if the final product includes quarks and quark bars, and in this case, the gamma rays is actually the flux is actually quite high, because you also have a contribution from the galactic dark matter. And you see the gamma ray flux is extended to the around 100 TeV or something like that. So that in this case, you have depending on model, you have a tension with existing Fermi gamma ray constraint, and this is demonstrated at this plot. And here is this is the dark matter mass, and this is the dark matter lifetime constraint, and this is the constraint pressed for the neutrino data, and this is the constraints from the pressed for the Fermi data. And this is the constraint coming from the air shower array experiments. And then, you see that, three limits are more or less comparable. And this implies that three messengers give the complementary constraints on the dark matter. OK, so using the 10 minutes, I think that finally I'd like to talk about the recent news about transient. So yes. So one of the biggest news in what happened in last year is a discovery of the IceCube 700922A. And this event is a very high energy event. The energy of neutrinos is around 300 TeV. And astronomers actually responded this event very quickly. And for example, the Japanese people use the data in the optical telescope. And using the brazier catalogs, they try to look for the Fermi data, and they found that the TXS brazier is flaring. And the Swift of satellites also made a follow-up observations very quickly, and they found different brazier candidates, and one of the TXS 06, 05, 06, 056. This is the brazier and the AGN, and also flaring. And when the neutrinos happen, and yes, gamma ray data and X-ray data show the high state. So this is kind of interesting because significance 3 sigma, but I would say that interpretation is under debate. Because yes, for this kind of business, it's very important that we were able to make a follow-up observation at different wavelengths. Yes. The neutrinos observed, then if you just simply plot the best kind of just one event. One event is very hard to say, but it's upper limit. But if you plot the best fit in here, and then with upper limit, and then we also have a gamma ray flux, and ultraviolet flux, and X-ray flux. And the important fact that we see the very beautiful dip, the valley in the X-rays. And then this actually constrains the model a lot. Again, the same story. If you want to expand these neutrino data, and then gamma rays are produced, the blazars are so bright, right? So a lot of photons exist, and gamma rays cannot get out, and the gamma rays interact with the low energy photons and cause electromagnetic cascade. And electromagnetic cascade flux actually it's a comparable the flux to the neutrino flux because the energy the neutral pions. The charged pions, the ratio is more or less similar. And then basically the X-rays, if you want to explain this neutrino data, the associated cascade flux actually fills the gap. The problem, you violate the data. So in order to satisfy these X-ray data, you can place limits on the neutrino flux, which is here. And then you can translate this limit is actually the neutrino event, right? This is 0.02 per year, 0.2 per year. And then, yes, so you see the difference. So if you want to explain the neutrino data in this simple model, you have to say that this event is lucky, more or less. I don't exclude. It's possible, because one event. And also, if you believe that this data, that you have a kind of a similar problem, in principle, that these gamma rays can be explained by the hadronic gamma rays, but this doesn't work. Same reason, because if you want to explain this neutrino data hadronically, and then basically if you want to explain the gamma ray data by pion decay, but this associated gamma ray flux actually try to fill the dip. so it doesn't work. So this means that if we want to explain the SED plus this neutrino data, it's quite challenging for the hadronic model to explain the two messengers. The situation is even worse for the other flaring event, because IceCube neutrino is found in the 2017, but they try to look for the data in past data. And they found more events in the 2014 to 2015. They found 13 events, which corresponds to 3.5 sigma, looks quite interesting. But the same problem happens. Neutrino data here, and if you look at this data in the gamma rays, yes, gamma data do not show flaring, and X-ray data also, we just have upper limit. And then if you calculate the gamma rays, X-rays corresponding to these neutrino flux, if you want to explain this data, you always violate X-ray data. So in this sense, if you consider the standard picture of the blazars, so far we don't have any simple picture to explain this neutrino data. So people now, because we don't have a simple concordance picture, and because of the X-ray constraints, and also another problem is if you want to explain the neutrinos, you have to put a lot of protons. And then this is also an analytics problem. And then we don't have a good solution. And people actually start to work on the complicated models. But I think the important thing is that we need to wait for more data to whether we address this kind of blazar as a real source of neutrinos or not. OK. So this is the story of the TXS. And yes, so we need more data, but transients in general are very appealing. Because yes, we just talk about blazars, flares. But in the case of transient, using neutrinos, you can point the position, plus you can use the timing information. These two kinds of informations enable us to reduce the atmospheric background significantly. And then in this sense, yes, so even IceCube, if we wait for a while, we have a still chance to see the neutrino transient. And then indeed, if you look at the possibilities, the many transients are actually found, including gamma ray bursts, supernova, double neutron star mergers, and tidal disruption events. So in the experimentaries, it's very important, to keep the continuous search. Then, in the sense, actually, one of the ongoing multi-messenger attempts is, kind of combine the different messenger. And the Penn State is leading one of the projects, so-called the Astrophysical Multi-Messenger Observatory Network. So the idea is that we do not want to miss any interesting neutrino gravitational wave event. So let's say that sub-threshold event. So that if you just see the one neutrino event, it's usually difficult to claim discovery. But if you have this neutrino event is correlated with a gamma signal or X-ray signal within a very short time window, actually you can actually claim you can estimate the significance, right? This can be a very important lead study model discovery. And then this is the idea. Then you can do this kind of apply this idea to the gravitational wave observations. Basically, we are developing the pipeline for the subthreshold analysis. For example, we have developing the pipeline on combining the IceCube neutrino data and the Fermi data or Hawk data, and then I try to analyze in real time, and we send the kind of real-time alerts based on the joint analysis, and astronomers can decide whether they want to make a follow-up observations, and then this can be the kind of opens the new opportunities to find this kind of neutrino gravitational wave transients. And what is the future? And AMO is a kind of near future attempt, and more far futures. And yes, so probably one of the important questions is to address what is the origin of the high energy cosmic neutrinos. Yes. So the people are now planning the IceCube Gen 2, which is 10 times bigger than IceCube in volume. And then we expect that angular resolution is also improved. Once you have this kind of the IceCube Gen 2, that actually I think it's kind of promising to address the problem of the cosmic neutrino origins, because I already showed that IceCube have a limit, and then disfavors the rare classes of the sources. But once you have Gen 2 with good angular resolutions, and in this case, this kind of the limits or the sensitivity is actually down to here. So at least, as far as I know, the models which are proposed in the literature can be tested once we have Gen 2. In this sense, our next Gen 2 and the ChemistryNet, because the ChemistryNet has a good angular resolution, this kind of the two experiments will are promising for us to address the question about the origin of the high-energy cosmic neutrinos. Okay, this is a summary. So yes, so the IceCube, and we detected the high-energy cosmic neutrinos. Even though we have not identified, we don't know the bulk of the origin. And the important fact is that neutrino flux is somehow comparable to the gamma ray flux and the cosmic flux. This might hint that in kind of connections among these different sources. Blazars gamma ray bursts are likely to be subdominant in the bulk of the high energy diffuse flux. Then maybe the galaxy clusters or starbursts might be responsible for the neutrinos above 100 TeV energy range. And this is interesting because this class of the sources can, in principle, explain the three messengers simultaneously. However, one interesting problem happens that neutrino data below 100 TeV is actually somehow very high. And this is more challenging. So that if this is real, we will need some hidden cosmic accelerators, such as AGN cores. And then this kind of multi-messenger information is quite useful for the dark matters. I didn't have time to talk about other possibilities, but you can actually probe the different types of the BSM interactions, and it can be also interesting. And the transient, yes, so even IceCube, we still have a chance to find interesting event. Yes, TX is a kind of the example. At least we don't have any simple picture, but at least this demonstrates that multi-messenger observations triggered by the neutrino events are now feasible. We can do that. And then we are planning, so probably we try to push these directions. In futures, maybe we try to have a kind of more strategic follow-up approach. For example, the AMON and the other attempts. Thank you very much.
Thank you, Kohta. So, questions?
Can you say a little more? What is a blazar?
Oh, the blazars, again, the active galactic nuclei, the supermassive black hole there, and then you have jets, right? So some of the AGN, active galactic nuclei, have jet. Then when you observe a jet from the on-axis, right? So yes, so this is a black hole. Then you have disk, and then you have jet. And then when you see the jet from here, and then blazars. And in this case, we see that because the jet is relativistically moving, and then you can observe the boosted emissions. Basically, the emission is actually boosted toward this direction.
So it comes out the axis that the black hole is spinning or something, and it's the axis of the black hole?
Yes, people expect that the black hole is rapidly rotating, and then basically jet is produced by this kind of black hole energies, rotation energy is extracted by the Brown-Husson mechanism for other stuff.
So, Kohta, at least in the case of clusters of galaxies,
Hi.
it is true that there is this confinement effect, but at the same time, the Fermi observations already put severe, very severe limits on the amount of energy you can have there, to the level of fraction of a percent. So this idea can work only with very hard spectra of the particles, but if the spectrum is very hard, then the neutrinos are the wrong spectrum. So I think the idea is just ruled out already.
No,
for many
we
years.
checked this. Actually, the spectrum is, yes, has to be hard. And, but this is actually expected in the AGN scenario. Because in the case of galaxy AGN, we have cocoons. So the low energy cosmic rays, actually, if you do the calculations, GB cosmic rays cannot get out because these are adiabatic losses.
Because of?
Adiabatic losses, because lobes is expanding. We have lobes, right? The lobes are expanding.
Yeah, but sooner or later they will expand. They will escape. I mean, adiabatic
escape,
losses
but
don't
probably,
mean that.
but still the low energy cosmic rays actually lose the energy for the adiabatic losses before they escape into the intergalactic medium. Now you know that this kind of radio lobes that has low density. And
Sure,
yeah.
but the lobe is already a megaparsec big or so, or several hundred kiloparsec big. So adiabatic losses can only be, a little bit. I mean, order unity. They cannot be just humongous energy losses. Otherwise,
no, this actually totally depends on where the particles accelerate. If you say that the particles accelerate in the very old stage, you are right. But if you think that for example, the cosmic rays accelerated when the jet is relatively like a Brazier regions or kiloparsec stuff, if you do the estimate, actually at least low energy cosmic rays, GB cosmic rays actually can be suppressed. That's the reason why we see this. And then here we actually evaluate this effect, and then here you see that spectrum is hard, right? Spectrum is hard here. Neutrino spectrum is quite hard, and then because GB cosmic rays actually is if you plot the cosmic ray spectrum, it is actually quite flat. And in this case, if you for example, I checked because I have a kind of calculation for the coma and the different nearby clusters, and it's totally consistent with his Fermi limits. And I think that for this kind of business, I think that to me is the more important information radio. Then the galaxy cluster case is okay, but gamma limits, I think it's fine. I can discuss later because I have a kind of plot for one more important thing for this kind of calculation, because of diffuse flux, right? And if you need to convolute the mass function of the AGN evolution and the mass function, and then actually AGN is the faster evolving, and the galaxy cluster is actually the kind of negative evolving. But still, because the AGN power is injected at a higher redshift, actually still many important contributions come higher redshift. Plus, and if you look at the most important mass range, actually this is order of the 10, not galaxy cluster range, not 10 to the 15 solar mass. Actually, the 5 times 10 to the 13 solar mass or something like that. This gives the bulk of contribution. So that if if you calculate the flux per the coma cluster, the massive clusters, actually you don't have to put a lot of cosmic rays in, inject a lot of energy per clusters. And then typically it's a kind of energetics is actually quite decent. Basically just 10% of the AGN and something like that, radio galaxies. So this actually in this sense. It's a bit also different from the typical prediction of the galaxy cluster because people usually put the gas mass, energy density ratio between the cosmic ray energy density pressure, gas density pressure. But the prediction is actually that distribution of the cosmic ray is more flatter, and this also gives a difference in the factor of hue. And basically, the several factor of hue is actually the enters, and you can check that limits are satisfied.
I have just a curiosity about this fascinating connection, the multi-messenger link. I wonder how much of it actually depends on your more or less hidden assumption about the spectra. Because to me, if I assume that the cosmic rays responsible for the neutrinos are I don't know, up to 10 to the 17 or 18 electron volts, this connection is gone, right? So, or for instance, that there is a lower energy cutoff, and so the gamma rays are, for whatever source of neutrinos is responsible for the observation, does not emit a lot of gamma rays below, I don't know, 50 or 30 TeV. How much of your linked constraints are relaxed?
Okay, so I think this is kind of it's a important question, and yes, there are. Okay, I would say in the simplest assumption, just power spectrum without any complications such as lobe confinement, whatever. In this case, parameter space is quite limited. Basically, as far as I know, for this kind of setup, in this case, the parameter is the spectrum index, and then just confinement energy scale of the cosmic rays, and then that's it. Basically, then you can actually adjust. You can try to fit the data. Then for the spectrum itself, basically the spectrum index has to be around 2.0, 2.1. In this simple case.
Independent of the cutoff or anything?
Yeah, cutoff is this low energy. What do you mean low energy?
Yeah.
This is a confinement scale, right? This cutoff.
I can give you a couple of examples. For instance, imagine that there is an extragalactic cosmic ray population,
Yes.
which only ends at, 10 to the 17.5 electron volt. Basically, we will never see this at Earth in the ultra energy cosmic ray, or very little of it.
Oh, you.
Huh?
Oh, you
And they will contribute a lot to the diffuse neutrino flux. So this is an example where I have a model where there is no link whatsoever between the ultra energy cosmic rays that I see.
Oh, this is totally possible. This is totally possible. But just but I want to say that if you are forced, for example, okay, I showed that this is a kind of original model. Actually,
Yes.
here is we try to explain the data around the 10 to the 17 electron volt when we don't explain the ultra high cosmic rays.
Yes.
And then you can explain the neutrinos, and you can still try to, gamma ray contribution is 1% of the, something like that, X-rated gamma ray. And then in this case, this is totally possible. Okay. But I just want my point is that if you want to explain, if you define the unified model in the sense that explain the ultra high cosmic data, neutrino data, gamma data. In this case, you cannot play a game a lot because the more data,
Sure,
more constraining.
But take the analogy of gravitational wave detection of coalescence of binary black holes. One of the fascinating aspects is that they have opened some window which was not possible to see in any other way. So we cannot exclude that actually IceCube is looking at some new class of objects which are not visible in ultra energy cosmic rays and are not visible in gamma rays.
Totally agree. So this is one of the possibilities, and which is appearing. Then, yes, you don't say that it's totally possible that neutrinos come from some tensors because IceCube neutrino PEB. The only thing you need is that cosmic rays accelerate 10 to the 17 electron volts. You don't have to accelerate cosmic neutron behind it. It can be totally decoupled. This is totally fine.
More questions? So I have a question about the connection. So you have a question? I have a question about this connection again, the same thing that Pasquale was asking. So I remember some time ago people were talking about neutrinos produced by the high energy cosmic rays. So this was called GZK neutrinos, which was kind of a floor. So where are these neutrinos in this plot? Okay, so for example, yes, actually you can see this. This is ZZK neutrinos, but here I assume the protons for simplicity. And then, this bump is actually the cosmogenic neutrinos, ZZK neutrinos. So we're not there yet? We have not detected, yes, because, this actually highly depends on the, the compositions and, other assumptions of the transition from the galactic to extragalactic components. So that if you assume that very conservative setup, I would say that if you want to explain the ultra high cosmic data above the anchor energies, and then if you want to fit the object composition data, in this case you require the mixed composition, and then in this case a predicted flux is around 10 to the minus 10, very low. Okay. Then it's not so easy. So the reason why, in this case, the flux is the order of 10 to the minus 9 is that because you want to explain the secondary component around 10 to the 17 electron volts by extragalactic component. If you want to explain the secondary component in the extragalactic component, automatically the neutrino flux has to be enhanced. That's the reason why then in the sense, depending on your assumptions and about the transition model compositions, prediction for the cosmic neutrino will change. Yeah. And then one of the important goals for the IceCube Gen 2 is that because IceCube sees this
And then IceCube Gen 2 probably can see the detail. And then the goal is to maybe you can try to access what happens around the 10 to the 17 electron volt, which is one of the important tasks of the Gen 2 and other future telescopes, such as the radio telescope, radio techniques and radio neutrino observatory, and GRAND, or some Cherenkov, techniques such as Trinity, and these kinds of experiments which are more suitable for the extremely high neutrinos may address this kind of question. Of course, it's not guaranteed.
Thank you. Some more questions for Kohta? So if not, let's thank Kohta again for this nice colloquium. There should be refreshments upstairs.
And for the students of the school, we will start 5 minutes later also because Kohta has to give the class, so he needs a little bit of rest after this amazing colloquium. Okay, come back in 15 minutes, students, and Kohta 5 minutes later.